Before we begin, the circuit diagram is important, and I think the biasing part is quite obvious here. Okay, we have the input bias and the output bias, and on the input we don't have any kind of current involved. We just have the voltage measurement. Okay, current is there, but then we are basically controlling it by voltage. So we have got VGS, that's the gate source voltage. At the output we have got the drain current. Okay, and then we have got the drain source voltage. So also remember the tap analogy that I've given you, and based on that we can understand that JFET basically works on a similar principle. So if we just look into the output characteristic, which is important because the final result, how does it behave, is more important here. And we can see that if we are basically varying the gate source voltage, for example, let's say we are increasing it, the depletion region is going to extend or increase in size or width. The reason is the input terminal is reverse biased, and if that increases, the drain current does not have that much of space to move around, as a result of which the drain current is restricted and we don't have that much current flowing. So this drain current can easily be controlled by the gate source voltage. So this is what we have seen in the principle of JFET, and if you plot a graph between the output drain current and the drain source voltage, we get a behavior which is something similar to a BJT. But then when we look into a BJT, this part is the current, the base current in case of a common emitter transistor. But here we are actually having the gate source voltage. So if we keep on increasing the voltage, the drain current will actually decrease. Okay. How? Because from the principle of working, it's reverse bias. So as we keep on increasing the voltage, the depletion region increases in width, the drain current reduces. Okay, so please don't get confused in exam. If you write down this as 1 volt, 2 volt, 3 volt, straight away you get a big zero. Okay, because that's not the principle. The entire principle is based on this. So if you keep on decreasing the voltage, the gate source voltage, the drain current is expected to increase. The point at which the drain voltage, okay, or the drain current starts becoming almost same, okay, throughout the region of the drain source voltage, we basically call it as the pinch off voltage. Okay, so these are some important points. Okay, and maybe we can just write down some points on this. Okay, so just points to note, okay, and these points will actually work out, okay, because this is important. Okay, so the drain current, I'll just write down few points here. Drain current ID, okay, rises with drain source voltage, right? With maybe I can just take the subscript. ID rises with the drain source voltage, okay, and then becomes constant. So the drain source voltage, okay, above which the drain current becomes constant, is actually called the pinch off voltage. Okay, so I'm just going to write down the definition later. Okay, so in this particular case, OA, or let's say O, okay, I'll just write down it as OA, is the pinch off voltage. Okay, so if I can just write down an A here, I think this will be more clear. So this is OA. Okay, OA is the pinch off voltage. Okay, and one more point to note, I think, is after pinch off voltage, after the pinch off voltage, the channel becomes very narrow. Okay, so it basically becomes very narrow. Okay, and the depletion region can almost touch each other. Okay, so the depletion region almost touches each other. So if it's so narrow, the chances of charges flowing will be minimum. Touches each other. the amount of charge that flows now will be more or less constant, and as a result of which we can say that the current is constant here. Okay, so drain current remains constant. Drain current then remains constant. Okay. Okay, so there are certain terms that we should actually know in connection with the output characteristics. Okay, and this is something which we are going to deal with now. Okay, so important terms. Okay, so let's just look into some important terms, and let me just list down the terms that we should know. Okay, the first thing is pinch off voltage, pinch off, and whenever you ask you in exam, you're probably going to write down the definition for that, and this is something which I'm going to give you. Okay, and then shorted gate drain current. Okay, not shorted drain current, and then we have got the gate source cutoff voltage. So how do we denote it? Before that, I think here I have just missed out the notation here. So this is VD ID, sorry. Okay, and then we are talking about the drain source voltage with drain source voltage. Okay, so the drain current ID rises with the drain source voltage. So this part will increase, this will also increase up to a certain point, and then it becomes a constant. So what happens, usually framing these sentences is easy if you can just remember the figure, and then of course you can just do it accordingly. Okay, so pinch off voltage is usually denoted by VP. Okay, shorted gate drain voltage current, sorry, is represented as IDSS. Okay, and then we have got the gate source cutoff voltage, so it is gate source, and since we are having a cutoff term here, just put a name as off. Okay, VGS off. Okay, so these are some important terms that we should know. Okay, and then probably we can just write down the definition for these. Okay, so the first to be nothing but the pinch of voltage. So if you remember the figure from there, we can actually identify what is pinch of voltage, but then let me just put it in words. Pinch of. Okay, so this is, you can say, the drain source voltage above which, okay, the drain current, okay, so the drain source voltage, the DS voltage, okay, above which the drain current becomes constant, okay, is known as the pinch off voltage. If you just write out the definition of pinch off voltage, you can probably do this, and then you can probably draw this figure and then show OA as the pinch off voltage. Okay, so that's there. So please be very elaborative when you are actually writing down your answers in your exam, because even if you make some figures explaining some terms, it basically helps to understand that you've actually got the topic clear. Okay. Okay. So the next is shorted gate drain current. So what I'd suggest is all of you please try to practice these things once or twice. Okay, because it's easier said than done, but then when you just look into the images, it looks like, okay, it's simple, I can remember, but then if you don't practice it, somehow you miss the entire point. Okay, so that's important. Okay, so let me just write down this. Okay, here let me just write down the first definition and then we can go. It is the drain current with some with source, sorry, with source shorted. So the source is being shorted, okay, circuit to gate. So the gate source voltage is basically shorted. Okay, maybe you can write it down as short circuited. Circuited to the gate. Okay, to the gate. Okay, in general we can say that we're talking about as VGS to be 0. So if we don't have any kind of voltage at the input, okay, we're basically shorting it out. Okay, and drain voltage, okay, voltage, I'll just draw the figure for you, that is VDS, okay, equal to pinch of voltage, equal to pinch of voltage. So it is connected. Okay, so it is also called, basically also called zero bias, because we are not applying any kind of bias at the input, zero bias current. Okay, so maybe I can just write this down. Okay, or maybe we can just draw this figure once. Okay, and then I think it will be more clear. So let's draw the graph once again. Okay, but then this time we are just going to take one part of the graph. Okay, so let's write down ID here. Okay, maybe the unit will be in milliamps. Okay, you get the milliamps current here mostly, and VDS. Okay, so we have this across this end. Okay, and then maybe we will have it this way. Okay, and maybe this is your pinch of voltage. Okay, and then this is actually something which we get for VGS is equal to 0. Okay, and at some point if we are going to increase VDS beyond some value, we are actually going to go into the breakdown region. So this part is actually the breakdown region. Okay, breakdown. So it is something related with avalanche breakdown. This is at some point you are going to have a large number of charges flowing and basically destroying the device. So this is VDS max. Okay, usually whenever you are using JFET, you are basically using it in this region. Okay, so this is basically something which we call as the active region. Okay, so now let's just get back into the definition here. What happens is, it is the drain current with source short circuited to gate. So whenever you are basically going to consider the input terminal, we have got 0. So that means VGS will basically be 0. Okay, and then we have got the drain voltage. So that means VDS equal to the pinch of voltage. Okay, so if we just quickly draw a circuit here, okay, maybe circuits should not be drawn very quickly, it somehow doesn't give you a very good image. Then let me just draw it. Okay, so we have it here, and then this end we are not going to apply any kind of biasing. Okay, we're just going to connect it. So this is our gate, this is our drain, this is our source, and maybe we can take n channel. Okay, n channel type, and then this would be nothing but IDSS. Okay, so this is represented as IDSS, so this is your IDSS. Okay, so this is IDSS, and this part we don't have, and maybe this is the drain voltage that we are applying, and this is IDSS, the drain current that we have. Okay, and across this end we are going to have our VDS. Okay, it might be a bit small in your mobile screen, but you just take care of what I'm saying. Okay, so this is your VDS. Okay, so please look into this. This is basically called the short circuited current. Okay, and this is actually achieved when the input terminal with not having any kind of biasing. Since we don't have any kind of biasing, the channel will still be there, right? The channel, if you are just remember the channel that we talked about, this is the channel here. Okay, and if this is P, this is P, and this is N, what happens is between these channels the charges are there. If you are not going to apply any kind of biasing across these ends, these channels or the width of this depletion layer is more or less going to get fixed or not going to change. If it is not going to change, we are going to have the charges flowing across it, okay, and that charge which gives rise to the current is basically called the shorted gate drain current, okay, because at the output terminal you are applying a bias, okay. So if we just probably just go back okay, to this particular image, if you are not applying anything here and you are actually applying some kind of voltage here, you have the electrons flowing, you are not restricting it with the input voltage, so this current is basically IDSS, okay. So you have to just know the entire theory to understand this even more clearly, okay. So during exam, probably when you explain this, probably you can just write down this definition, okay. And this, also remember that this drain voltage that we are talking about, that means VDS, is equal to the pinch off voltage, okay. So we take this and we actually consider this as the active region, okay. So this is again important. So this particular region is again called the constant current region. So maybe I can just write down this definition. The region, okay, the region, and if I ask you to explain this graph, you should be able to write down these points, okay. The region between Vp and Vds max, okay, this is basically called the constant current region. Constant current region. I think this is quite obvious because the current is not changing here, okay, or the active region. Okay, and this VDS max, I think this is also obvious. This is actually the breakdown voltage. Breakdown voltage. Okay, this is the breakdown voltage. So please remember these terms, okay. It's actually quite obvious, but then you have to just study it in a sequence, okay. It's actually called the gate source cutoff voltage, and the idea is very simple. So it's the gate source cutoff voltage. So that's basically written as VGS off, and that is why it is called because it is called cutoff, so we just need to denote it a different way. It is the gate, I will just draw some figures and probably it will be clear. Gate source voltage, okay, where the channel is completely cut off, okay. That means you don't have any kind of charges flowing, okay, completely cut off, and the drain current becomes zero. Drain completely cut off and the drain current becomes zero, okay. So that is basically what we call as the gate source cutoff voltage, okay. And then maybe you can just draw a figure here, okay, the graph rather. And what happens is we are going to just reduce the voltage biasing, okay. So if we are just changing the biasing part, we are just going to get a cutoff voltage at some point, okay. So that means VGS, okay. So before I go to this, let me just go to that part, okay. So VGS is this, okay, gate source, this part. So you are basically going to apply some kind of biasing, okay, and if you just change the biasing part, okay, and then you are going to make the depletion region totally thick so that none of the charges can flow across, you're basically going to cut off the drain current here, okay. You're going to just have a cutoff region. So that is how it is written, and then we can actually write it down as minus VGS. This actually should curve here. Okay. This is VGS off. So it is totally cut off. We don't have any kind of current here. Okay, and I'm just going to compare it with a numerical problem. Okay, we're just going to do a numerical problem, and probably this is going to be more clear. So this is the gate source voltage. So this is the gate source voltage that we have. Okay, where the channel is completely cut off and the drain current becomes zero. Completely cut off means none of the current passes through. Okay, here what happens is usually this is actually comparable to the pinch off voltage. So if pinch off voltage is somewhere here, okay, at an equal distance on the other side of the negative axis, we are going to have the gate source cutoff voltage. Okay, so to understand this better, maybe we can actually just take one example. Okay, so let me just take one example here. Okay. And before I take that example, probably let me just give you another term which is basically called the drain current, expression for drain current, expression for or drain current relation, drain current. So how do you exactly measure the drain current based on what are the parameters that you have? Okay, so it is basically the relation between IDSS and VP. Okay, so it is the relation between IDSS and VP. So I am not going to do any kind of derivation for this because this derivation is kind of complicated, but we are just going to remember the relation for calculating this drain current. Okay, IDSS and VP. Okay, and what's the relation? The relation looks something like this. ID, which is the drain current, is IDSS. Okay, so at this point when we talk about IDSS, we are talking about a condition where the drain current is completely cut off. Okay, so that's important. 1 minus VGS divided by VGS off. Now this is the relation. Okay, square. Okay, so what are the terms here? We have the terms as ID as the drain current. Okay, and then we have got IDSS, which is, so you have to remember this and then accordingly use it whenever a numerical problem is given. Short circuited drain current, this will be actually given to you in case you are asked to find out the drain current. Okay, and then what else? VGS, gate source voltage, gate source voltage, and then we have got VGS off. Okay, so it is gate source cutoff voltage, right? Cutoff voltage. One more thing to note here is that what happens is this is basically the gate source cutoff voltage VG off, GS off. Okay, is basically equal to the pinch off voltage. Okay, is basically equal to the pinch off voltage. Okay, now but before I explain this, probably I can just go back here. Okay, and this is the diagram which explains everything here. Okay, so if we have got VGS as 0, okay, you're basically going to have some kind of electrons flowing. Okay, but then what happens is if you keep on changing the biasing on this side, you are going to increase this width of the depletion region, and at some point you are going to get a total cutoff of any charge carriers flowing. Okay, so this is something which is important to understand when we actually talk about the gate source cutoff voltage. Okay, so before that I think we can actually um, take an example, and probably I will just draw this figure, and from this figure maybe we can actually solve one numerical problem. Okay, so what I'll do is I will take on both ends. Okay, And on this side, okay, on this side we are going to have the drain current ID, and ID will become 0 at different conditions. Okay, so let's just keep this VDS here, that's in volts. Okay, and if we keep on increasing VDS, we are going to get the value. Okay, so maybe I can just I don't need the remaining part of it, I just need it up to the pinch of voltage. So let's say at this point we are actually going to have the pinch of voltage. Okay, so I will just take this to be VGS is equal to 0. So even if the gate source voltage is 0, you can actually get the current, drain current, depending on VDS. Okay, so this is your pinch of voltage. This diagram explains a lot. Okay, but on the other hand, if we just keep on changing the biasing of this, and we actually are going to the negative biasing, we are even going to completely cut off the current. We are not going to have any kind of current here. Okay, so the condition here is that at the gate source cutoff voltage. Okay, so you know, if VDS is also becomes 0, imagine this, if we just, so this is not there, and then the charges are flowing because you are having some VDS here, right? Now imagine this, you are actually reverse biasing it. Okay, and you are actually reducing the voltage. If you reduce the voltage further and further and you take it up to 0, even this current is not something which you are going to get. Okay, so that will actually depend on how do you handle VDS. Okay, so this is the cutoff voltage. So this much region and this much region is the same, it's the same. Okay, it just doesn't look up to that point in that scale. Okay, so this is a good example that we can actually take, and I can just write it down as minus of VGS in volts. Okay, so VDS is 0, VGS is taken to the minus scale, and then we are going to see that we are going to have this cutoff voltage. Okay, the question might be, write the equation for drain current. So the question for this is, write the equation for drain current. Drain current. Okay, that's the question. Yeah, so this graph might be given, and you know the values will be given to you. Okay, so in that way you can actually write down the equation of drain current. Okay, so let me just uh, take a figure where I can give you some values. Okay, so just wait. Okay, so maybe something like this. Okay, so this is, let's say, 12 milliamps. So if you are given a value and you have to write down the equation for the drain current, probably some figure will be given and there will be some values which will be provided, and this is minus 5 volt. Okay, and this is minus VGS. Okay, this is off, or not off. Okay, just not take this. Okay, so you have to write down the relation here for this particular image. What you can do is you can just simply write it down, what is IDSS, which is nothing but 12 milliamps. Okay, and then you can actually write it down as VGS off, which is given to be minus 5 volt. Okay, so this particular value is here, which is already being provided to be minus 5 volt. Okay, and if I just want to write down what is the value of ID, I can just simply write it down. ID is equal to IDSS, so I can just simply write it down as 12. Okay, and then it is 1 minus, if you remember, on top we have got VGS, and at the bottom we have got VGS off. Okay, so at the bottom I can write it down as minus 5, on top I can just write it down as VGS, and this will be in milliamps. The reason is this is in milliamps, this is voltage by voltage, so this is just a ratio of voltage, so the unit doesn't matter, unit less quantity, so it's in milliamps, so I'll just keep this as milliamps. Okay, So if you just take this in this way, I can just simply write it down the expression as 12 into 1 plus VGS divided by 5 milliampere. Okay, so sometimes you might be given this figure and then you are probably going to write down the values. Okay, so please understand the difference between these three. We have got the pinch of voltage and this is your pinch of voltage. Okay, and then we have got the shorted gate drain circuit. So as soon as the term shorted comes in, that means at the input you are not going to apply any kind of voltage. At the output you will be having some kind of voltage. Okay, and based on that you are going to get the drain current. Okay, and that drain current is going to be here. So this is the constant current region. Okay, and finally when we talk about the gate source cutoff voltage, if we actually totally want to cut off the drain current, okay, what we have to do is we have to change the biasing of VGS in the opposite direction. Okay, and as we keep on decreasing it, and if we just go to around, let's say, -3 -4 volt, typically most of the times we don't have any kind of drain current flowing across. Okay, so that becomes totally zero. Okay, so that is there. So please remember this three terms, okay, which are important. What we are going to do in the next class is we had too much of interference today, okay, because of the power. What we are going to do in the next class is we are going to basically talk about some advantages of JFET. Okay, we are going to talk a bit about the biasing of JFET. Okay, and then finally we are going to finish the unit with MOSFET. Okay.